Our universe holds worlds stranger than any science fiction. Far beyond our familiar solar system, astronomers are now discovering entire planets orbiting distant stars. And these exoplanets are rewriting every rule we thought we knew. By the end of this journey, you will have toured 25 of the most bizarre alien worlds ever found. We will visit a planet where the sky rains molten glass and another that is quite literally made of diamond. How can a world survive being devoured by its own sun? And what does a planet with clouds of sapphire even look like? The cosmos is an artist of the extreme, and its latest creations are waiting to be revealed. What do you think is the ultimate limit for how strange a planet can be? The journey begins with a world of unimaginable luxury and brutal extremes. Orbiting a star 50 light-years away, the planet 55 Cancri E is a super-Earth, a world several times larger than our own, but it bears no resemblance to the blue marble we call home. This planet circles its sun-like star so closely that an entire year lasts just 18 hours. Imagine a world where a birthday comes every single afternoon. Such proximity creates a hellish environment. Daytime temperatures soar beyond 4,000 degrees Fahrenheit, hot enough to vaporize iron. This furnace of a world is also tidally locked, meaning one side forever faces the star's blistering glare, while the other is trapped in eternal, though still scorching night. But the true wonder of 55 Cancri E lies beneath its incandescent skin. Astronomers believe its core is not rich in oxygen and silicates like Earth, but is instead packed with carbon. Under the immense pressures and searing heat of this world, that carbon could have crystallized into a layer of diamond hundreds of miles thick. We are likely looking at a planet with a mantle of solid diamond, a glittering core of unimaginable wealth floating in the void. The surface itself is a mystery, possibly a shifting crust of graphite and silicon carbide, dark and strange. For years, scientists thought such a world would be airless, its atmosphere boiled away by the stellar inferno. Then the James Webb Space Telescope turned its gaze toward it. To everyone's astonishment, it detected signs of a substantial atmosphere clinging to this diamond world. This shroud could be a thick blanket of carbon dioxide, or perhaps something even more alien, a gaseous haze of vaporized rock and silicate particles, creating a permanent global fog of molten stone. This discovery transforms 55 Cancri E from a static jewel into a dynamic, breathing world of diamond and smoke, where the very sky might be made of vaporized gems. It is a stark reminder that the universe's treasures are often forged in the most violent of fires. Yet the diamond world's blistering heat is not the universe's only form of fury. If you could stand on the cobalt blue world of HD 189,733b, you would witness a storm of unimaginable violence. This planet is a gas giant, similar in size to Jupiter, but its beauty is a deadly illusion. From a distance, it shines with a deep, serene azure, a color that comes not from oceans, but from a hazy atmosphere thick with silicate particles. These tiny fragments of rock and glass scatter blue light across the sky, painting the entire world in a deceptive calm. The reality on the ground, if there were ground, is pure chaos. HD 189,733b orbits so close to its star that a year is a mere 2 Earth days, and the surface temperature is a constant 1,700 degrees Fahrenheit. This furnace heat vaporizes the silicate particles in its upper atmosphere. Then, the planet's weather takes over. Winds scream across the atmosphere at over 5,000 miles per hour, many times the speed of sound here on Earth. These aren't breezes. They are supersonic rivers of scalding gas. Here is where the blue sky turns into a nightmare. The furious winds whip those vaporized silicate particles into a frenzied global storm. As the particles are carried to slightly cooler, higher altitudes, they condense. They do not form water droplets. Instead, they coalesce into droplets of molten glass. And then, propelled by those incredible winds, this glass rain falls. It does not fall down. It flies sideways, a horizontal barrage of scalding liquid shards moving at bullet speeds. This is a world where the sky itself is a perpetual, abrasive sandblaster of molten rock. A beautiful blue hellscape where simply existing would mean being flayed and melted in an instant. It makes a diamond crust seem almost tranquil by comparison. Even that world of sideways glass seems almost gentle compared to the next spectacle. WASP 76b is a planet where the sky does not merely rain molten rock, but pure liquid iron. This is an ultra-hot Jupiter, a gas giant orbiting so perilously close to its star that it completes a full orbit in less than 2 Earth days. The punishment for this proximity is absolute. On its permanent day side, the side forever staring into the stellar furnace, temperatures soar beyond 4,000 degrees Fahrenheit. At that kind of heat, nothing solid can survive. Metals do not just melt, they vaporize. The very atoms of iron are ripped from the surface and lofted into a searing, metallic atmosphere. Here is where the planet's weather system, a nightmare of thermodynamics, takes over. The day side is an unrelenting blast furnace, while the night side, shrouded in eternal darkness, is comparatively cooler, though still hot enough to melt lead. This staggering temperature difference, thousands of degrees across a single world, creates supersonic winds. These are global jet streams of unimaginable power, screaming from the scorching day hemisphere to the slightly less scorching night. They carry with them the vaporized iron. As this metallic fog is violently shoved into the relative chill of the night side, it hits a point where it can no longer stay a gas. The iron condenses. It forms clouds not of water, but of liquid metal. And then it falls. On the night side of WASP 76b, it perpetually rains droplets of molten iron. Scientists did not just theorize this, they saw it. Using a technique called spectroscopy, which analyzes the starlight filtering through a planet's atmosphere, they detected the clear chemical signature of iron vapor on the hot day side. But on the boundary of the terminator, the line between day and night, that signature vanished. The iron was simply gone, having condensed and precipitated out of the atmosphere. This confirmed the cycle, a brutal metallic water cycle where the evaporation, transport, and precipitation are all performed by a single element under extreme duress. It is a world with a liquid core of molten iron, like Earth, but with the shocking difference that its core is also in its sky, falling in an endless, incandescent drizzle upon a landscape of eternal twilight. From a world of metallic rain, we move to one shrouded in a perpetual global steam. GJ 1214b is a celestial enigma, a world that defies easy classification. Discovered orbiting a dim red dwarf star 40 light-years away, it sits in a category all its own, somewhere between a super-Earth and a mini-Neptune. Its size and mass tell a curious story. While it is about 2.5 times wider than our planet, its overall density is remarkably low. This is the crucial clue. A density that low cannot be explained by a solid, rocky world like Earth, or even a gaseous one like Jupiter. Instead, the numbers point to a composition rich in something much lighter, something that makes up most of our own world's surface, water. CJ 1214b is one of the strongest candidates we have for a true water world. But this is not an ocean planet as we might dream of it. The conditions here are utterly alien. Imagine a planet where the entire surface is not land, but a single planet-wide ocean, hundreds of miles deep. The pressure at the bottom of such an abyss would be crushing, millions of times greater than at the bottom of our Mariana Trench. Under that incredible weight, water does not behave like the liquid we know. It is compressed into exotic, high-pressure forms of ice, not cold ice from a freezer, but hot ice. Scientists call these phases Ice 6, Ice 7, or Ice 10, solids that form under tremendous pressure even at searing temperatures. So the structure of this world could be layered like a cosmic onion, a steamy, thick atmosphere giving way to a global ocean of liquid water, which then transitions into a mantle of hot, solid ice, all surrounding a small, rocky core. The atmosphere itself is a frustrating mystery. Observations show it is thick and uniform, likely shrouded in a high-altitude haze or a global layer of clouds that stubbornly blocks our view of the layers beneath. This veil makes it impossible to see what the surface conditions are truly like. Is it a supercritical fluid, a state where liquid and gas become indistinguishable? Is it a perpetual, scalding steam bath? We simply do not know yet. GJ 1214b represents a profound puzzle, a world made almost entirely of the most vital compound for life, yet organized into forms and under pressures so extreme that they remain almost pure speculation. It is a reminder that an ocean planet is not necessarily a welcoming one, but a realm where the very nature of water is transformed into something alien and strange. But the universe's imagination stretches beyond single suns. Some worlds are born into a double dawn. Orbiting a pair of stars 200 light-years away, Kepler 16b is a gas giant that science fiction fans instantly recognized, a real world mirroring the iconic twin sunsets of Tatooine. This planet does not orbit a single star. It gracefully circles both members of a binary pair, a stellar dance partner locked in an 80-day orbit around each other. Planets like this are called circumbinary, and for a long time, they were thought to be nearly impossible, their orbits too chaotic to survive the gravitational tug-of-war between two stars. Kepler 16b proved that not only could they exist, but we could find them. The Kepler Space Telescope discovered it using the transit method, watching for the tiny dip in starlight as a planet passes in front of its star. But here, the data was a puzzle. The light from this system didn't just dim in a simple, periodic pattern. It dipped at irregular intervals, sometimes deeper, sometimes shallower, and sometimes the dips vanished entirely. Astronomers had to untangle a celestial rhythm section. They realized they were seeing the planet transiting not one, but two different stars, each eclipse blocking a different amount of light depending on which star was being crossed. It was like listening to two overlapping drumbeats and discerning the single, steady walk of a planet keeping time around them both. The world itself is cold and distant, a Saturn-sized giant orbiting far from its twin suns, where surface temperatures plunge to 100 degrees below zero. Its skies, however, would offer a forever changing spectacle. The two stars, one orange and one red, dance closely together in the sky, casting complex, shifting shadows and creating sunrises and sunsets with multiple phases of light. While its frozen gases offer no hope for life as we know it, Kepler 16b is a monument to cosmic stability, a planet that found a perfect, wide path in a gravitational minefield. It stands as a powerful testament that even the most fantastical scenes from our stories are waiting patiently in the data. Yet even the most stable orbits can hide profound mysteries of light and shadow. In the constellation Draco, a world named Tarius 2b holds the title of the darkest planet ever discovered. This is a gas giant, similar in size to Jupiter, orbiting a star 750 light-years away. But if you could see it directly against the blackness of space, you would struggle to make it out. TRES 2b reflects less than 1% of the light that hits it. That makes it blacker than coal, blacker than a pool of ink, blacker even than a freshly paved asphalt road on a moonless night. It is a void in the shape of a planet. How can something so large absorb almost every single photon that touches it? The answer is not simply the absence of light, but the presence of a truly alien atmosphere. Unlike Jupiter or Saturn, which are banded with bright, reflective clouds of ammonia, this world appears to have no such reflective layers. Its atmosphere is likely devoid of these bright aerosols, creating a deep, clear, and terrifyingly efficient light trap. But scientists believe the darkness goes deeper than missing clouds. The atmosphere of TRES 2b is a scorching 200 degrees Fahrenheit, hot enough to vaporize exotic chemicals. It may be rich in light-absorbing substances like gaseous sodium and potassium, or perhaps even titanium oxide, a compound used in paints here on Earth to make them ultra-white, but which in a gaseous form at these temperatures could act as a phenomenal light sponge. These elements would not just dim the light, they would greedily swallow specific wavelengths, leaving almost nothing to bounce back to an observer's eye. This creates a profound paradox. While the planet is darker than any known natural surface, it is not completely invisible. Its proximity to its star heats its atmosphere to an incredible glow. TRES 2b emits a faint, deep red radiance, like a colossal ember drifting through space. This is not reflected light, but its own intrinsic thermal radiation, the dim blush of its own scorching heat. To discover a world like this, astronomers did not look for a dimming star, but for the subtle, periodic dimming of this faint red glow as the planet circled behind its sun. It is a world defined by absence, a silhouette that burns from within, reminding us that in the cosmos, darkness can be just as active and luminous as any sun. Our darkest world orbits a living sun, but some planets circle the dead. The story of exoplanet discovery does not begin in a gentle solar system, but in a cosmic graveyard. In 1992, astronomers made a historic announcement. They had found the first confirmed planets beyond our solar system, and they were orbiting a corpse. The star system PSRB 1257+12 is centered on a pulsar, the super-dense, rapidly spinning remnant of a colossal supernova explosion. This object is a neutron star, a city-sized sphere containing more mass than our sun, spinning hundreds of times per second and blasting out a lighthouse beam of intense radiation with every rotation. It is the last place anyone expected to find a family of planets. The very violence that created this pulsar should have vaporized any worlds that once existed. So how did they get there? The leading theory is a story of stellar cannibalism and rebirth. This pulsar likely had a companion star, a binary partner. When the more massive star reached the end of its life, it exploded in a supernova, its core collapsing into the pulsar we see today. The blast would have severely damaged or even destroyed the companion star, shredding it into a vast, swirling disk of debris. From this disk of stellar ashes, in the chaotic aftermath of a stellar death, new planets coalesced. They are second-generation worlds, born from the ruins of a cataclysm. Detecting them required genius, Astronomers did not look for a wobble or a dimming of light. Instead, they listened to the clockwork rhythm of the pulsar's radio beam, a pulse so regular it rivals atomic clocks. They noticed tiny, systematic variations in the timing of these pulses, arriving a fraction of a second early or late. The only explanation was the subtle gravitational tug of orbiting bodies, pulling the pulsar back and forth in space. By decoding this exquisite timing dance, they revealed not one, but at least 3 small, rocky worlds in this system. These planets are unlike any in our neighborhood. Bathed in intense radiation and circling a dead star, they are likely barren and strange. Given the carbon-rich debris from which they formed and the immense pressures they might endure, scientists speculate their cores could be crystallized carbon, making them diamond worlds on a scale far beyond 55 Cancri. They are monuments to cosmic resilience, proof that planets can form in the most hostile environments imaginable, rising like phoenixes from stellar ashes. This pulsar system was our first glimpse into the true diversity of the cosmos, a signal from a graveyard that told us the universe was far more creative and far more stubborn than we ever dreamed. That faint red glow of a dark world is a whisper next to the screaming radiation of the next. Kelt 9b is not merely a hot planet. It is the hottest world ever discovered, an ultra-hot Jupiter that exists in a state of perpetual disintegration. Orbiting a massive, blue-white star 650 light-years away, this planet is so close to its sun that a full year is a blistering 36 hours. The dayside temperature soars beyond 7,800 degrees Fahrenheit, a heat that does not just melt metal, it vaporizes molecules. This world is literally hotter than the surface of some red dwarf stars. Its host star, a type of star, burns ferociously and emits a torrent of high-energy ultraviolet radiation. Kelt 9b is so close that it is being cooked and stripped bare by this stellar fury. The extreme heat puffs the planet's atmosphere up like a balloon, making it nearly twice the size of Jupiter despite having only half the mass. But that inflated atmosphere is under constant attack. The ultraviolet radiation from the star is so intense that it acts like a cosmic blowtorch, blasting atoms from the planet's upper layers and hurling them into space. This creates a vast, glowing tail of lost material that streams behind the planet as it orbits, making it resemble a giant, doomed comet. Observations with the Hubble Space Telescope have confirmed this evaporation, watching the spectral signature of hydrogen being torn away. The atmosphere itself is a dissociated soup of atomic elements. On cooler worlds, atoms bond to form familiar molecules like water or carbon dioxide. Here, the heat is too great for such bonds to hold. Using powerful telescopes, astronomers have detected the signatures of vaporized iron and titanium in the atmosphere of Kelt 9b. But they are not detecting iron oxide or titanium dioxide. They are seeing the individual, solitary atoms of these metals floating freely in the scorching air, a clear sign of a world where chemistry as we know it has been utterly shattered. Every orbit, Kelt 9b loses millions of tons of its atmosphere. The question is not if this world will be destroyed, but when. Depending on its initial mass and the relentless power of its star, it could be completely evaporated over hundreds of millions of years, leaving behind only a scorched, barren core. Or its outer layers may be stripped away to reveal a previously hidden super-Earth heart. It is a planet living on borrowed time, offering us a front-row seat to the final, violent act of a world being slowly unmade by its own sun. The blistering fate of Kelt 9b shows us a world being actively destroyed. But what happens after the destruction is complete? orbiting a star 730 light-years away. 2I-849b is the ghost of a giant. This world is a profound mystery, a planet that should not exist according to our standard models. It is roughly the size of Neptune, yet it possesses a staggering density. While Neptune is a fluffy, low-density ice giant made mostly of swirling gases over a small core, 2I-849b is the opposite. Its immense gravity and measured mass reveal a composition that is almost entirely solid rock and metal. It is as if someone took the planet Neptune, somehow peeled away 95% of its volume, and left behind only its dense central heart. This is why astronomers call it a likely Chthonian planet, a name taken from Greek mythology for gods of the underworld, representing a world that has been stripped down to its bare, primordial core. The leading theory is a story of migration and stellar robbery. This world likely began its life much farther out in its solar system as a fairly standard gas giant, a Jupiter or Neptune-like world with a thick, deep envelope of hydrogen and helium. But something went wrong. Gravitational interactions with other planets or the protoplanetary disk may have sent it spiraling inward on a death plunge toward its star. As it migrated too close, the intense radiation and stellar winds began to tear away its gaseous shroud. Unlike Kelt 9b, which is currently in the process of losing its atmosphere, 2I-849b appears to have completed the process. Its entire massive atmosphere was completely stripped away, leaving behind only the colossal solid core, a naked, scorching relic exposed to the vacuum of space. This makes it a unique archaeological site, a chance for scientists to study the interior of a gas giant directly, something we can never do in our own solar system. What does the core of a giant look like? It might be a searing landscape of solidified metal and silicate rock, under pressures so intense that matter behaves in ways we can barely simulate. It is a planetary fossil, a monument to stellar violence that offers us a glimpse into the hidden hearts of the most common large planets in our galaxy. From the colossal stripped core of a giant, we now shrink down to a dense, metallic bullet of a world. J367b is a planet that defies all expectations for a rocky body. Discovered orbiting a dim red dwarf star just 31 light-years away, this tiny world is only about 70% the size of Earth, making it roughly the dimensions of Mars. But its mass tells a completely different story. Despite its small stature, it is astonishingly heavy, packing about 55% of Earth's mass into that smaller frame. The math reveals an incredible density, far greater than our own planet's. This can only mean one thing. J367b is not a world of rock and mantle. It is a planet made almost entirely of metal, likely an iron core with only the thinnest veneer of silicate rock. It is a scaled-up, superheated version of Mercury's oversized core, but taken to an even more extreme conclusion. This metallic marble exists in a state of perpetual, frantic motion. It orbits its quiet red dwarf star at a breathtakingly close distance, completing a full year in just 8 hours. You could celebrate a new year with every single work shift. This proximity creates a furnace on a planetary scale. The estimated surface temperature is a blistering 2,700 degrees Fahrenheit, a heat so intense it is well above the melting point of iron. This presents a surreal and terrifying image, a world where the very ground beneath your feet, if you could stand there, would be a global ocean of molten metal, shimmering under the perpetual glare of a deep red sun. How does such a bizarre world come to be? Astronomers believe its story is one of catastrophic violence. GJ 367b likely formed much farther out, as a more typical rocky planet with a balanced mix of silicate rock and a metallic core. But in its system's chaotic youth, it may have suffered a series of colossal collisions, cataclysmic impacts that blasted away its lighter outer rocky mantle, leaving behind only the dense, heavy heart of iron. Alternatively, it might have migrated inward from a cooler birthplace, and its searing proximity to its star simply vaporized and stripped away its rocky shell over eons, leaving the metallic core exposed. This tiny, ultra-dense world is more than just a curiosity. It is a crucial laboratory. By studying its extreme properties, scientists can test the very limits of planetary formation and evolution. It asks profound questions about what happens to terrestrial worlds under the most severe conditions, how much punishment a planet can take before it is reduced to its elemental essence. JJ 367b stands as a metallic testament to the fact that even small, quiet stars can host the most extreme and unforgiving of worlds. There is a world whose very shape is a testament to its imminent destruction. WASP-12b is a hot Jupiter orbiting so perilously close to its yellow dwarf star that it completes a full orbit in just over one Earth day. This proximity has triggered a cosmic death spiral. The star's immense gravity does not just pull on the planet, it actively distorts it, stretching the gaseous giant into a pronounced egg shape. This is not a stable configuration. The planet is so close that it has crossed a critical boundary known as the Roche limit, the point where a star's gravitational pull overwhelms the planet's own gravity holding it together. The result is a process called Roche lobe overflow, a slow and spectacular act of stellar cannibalism. The star's gravity is literally siphoning material directly from the planet's bloated atmosphere. This stolen gas does not fall straight into the star. Instead, it spirals inward, forming a thin, hot accretion disk of planetary material that encircles the star like a cosmic drain. We are witnessing a planet being eaten alive, its essence drawn out into a glowing ring before being finally consumed. Adding to its eerie profile, WASP-12b is also incredibly dark, reflecting less than 6% of the light that hits it. Observations from the Hubble Space Telescope revealed another layer to its strangeness. Its atmosphere shows clear signs of carbon-rich chemistry. It contains methane and other carbon-bearing molecules, but in a surprising twist, it appears to have far more carbon than oxygen. This suggests a world that might be rich in carbon compounds, a stark contrast to our own oxygen-dominated planet. So we have a bizarre portrait, a carbon-rich, egg-shaped world, darker than asphalt, actively spilling its guts into a glowing disk around its devouring sun. It is a stark and beautiful reminder that in the cosmos, even a giant planet is not safe from the hunger of its own star. Such a dense metallic world seems to defy the laws of physics, yet another planet challenges the very rules of how worlds are built. Kepler-10c was a discovery that sent shockwaves through astronomy, a cosmic puzzle orbiting a sun-like star 560 light-years away. This planet is a super-Earth, but that label feels utterly inadequate. It possesses a staggering 17 times the mass of our own world. According to all conventional models, a planet that massive, forming that close to its star, should have used its powerful gravity to vacuum up enormous amounts of hydrogen and helium during its birth, ballooning into a gas giant like Neptune or even Jupiter. But Kepler-10c did no such thing. Precise measurements of its size and mass revealed an astonishing truth. Its density is far too high for a gassy world. It is solid rock and metal through and through. Astronomers were forced to coin a new term for it, a mega-Earth. This is a colossal terrestrial planet, a rocky behemoth on a scale we thought impossible. Its very existence forces a complete rethinking of planetary formation. How did it gather so much solid material without also capturing a huge gaseous envelope? Perhaps it formed later in the life of its protoplanetary disk. After most of the light, hydrogen and helium had already dissipated, allowing it to accrete only heavy rocks and metals. Or maybe it is the massive core of a failed gas giant, a world that started to gather gas but had its gaseous shroud stripped away by the intense radiation of its young star, similar to the fate of TOI 849b, but stopping short of complete exposure. Adding to its intrigue, Kepler 10c is ancient. Its system is over 10 billion years old, meaning this mega-Earth formed when the universe itself was still in its relative youth. It has existed for more than twice the age of our solar system. This longevity suggests that massive rocky worlds can be stable over cosmic timescales, opening the door to the possibility of many more such giants lurking in the galaxy. Its companion in this ancient system, Kepler 10b, provides a stark contrast. A scorching, smaller lava world so close to the star that its surface is likely an ocean of molten rock. Together, they paint a picture of a system where planetary destiny was carved by violence and scarcity, resulting in one world of fire and another of unimaginably heavy, solid stone. Kepler 10c stands as a monumental correction to our theories, proving that when it comes to planet building, the universe has a far heavier hand than we ever anticipated. The mega-Earth is a world of solid, ancient permanence, but other planets live in a state of perpetual, chaotic flux. HD 80606b is a gas giant that does not orbit its star, it assaults it. This world follows not a gentle circle, but a wildly stretched oval, one of the most eccentric paths ever measured for a planet. For most of its 111 Earth day year, it drifts in the cold outer reaches of its system, a Jupiter-like distance from its sun. But then, its orbit whips it around in a terrifyingly close swing by. At its closest approach, or periastron, it ventures over 10 times nearer to its star than Mercury is to our sun. This isn't a graceful dance. It is a cosmic roller coaster dive into a furnace. The effects are apocalyptic. As the planet screams toward its star, the temperature of its atmosphere doesn't just rise gradually, it explodes. Observations from the Spitzer Space Telescope captured this event in infrared light, watching the planet's sun-facing side heat from a frigid 1,000 degrees Fahrenheit to a scorching 200 degrees in a matter of just 6 hours. That is a heating rate of over 500 degrees per hour. Imagine a winter day on Jupiter suddenly transforming into the surface of a lava world before lunchtime. This brutal and rapid heating does not create gentle breezes. It detonates global weather. The atmosphere on the blistering dayside expands violently, unleashing supersonic shockwaves that race across the entire planet. These are not storms as we know them, but planet-wide seismic events in the air, generating winds that may scream at speeds over 10,000 miles per hour, enough to shred continents of gas and vaporize any structure. The entire world roils with turbulence on a scale that defies comprehension. Then, as quickly as it arrived, the planet whips back out to the frigid depths of its orbit, and the atmosphere collapses and cools, only to be reignited again on its next deadly plunge. This is a world with a single, devastating season that comes and goes in a flash, a season of pure atmospheric fury. It is a stark lesson that a planet's path through space can be the most violent force of all. Such extreme orbits create worlds of fire and chaos, but others offer a stark and silent alternative. Just 49 light-years away, orbiting a quiet red dwarf star, LHS 3844b presents a very different kind of super-Earth. This world is almost exactly the same size as our own, a rare Earth-sized twin in terms of dimensions. Yet the resemblance ends there. When the Spitzer Space Telescope studied the infrared heat signature of this planet, it found something startling, or rather, a lack of something. There was no detectable heat being circulated from its day side to its night side. This simple absence of data speaks volumes. On a world with even a thin atmosphere, winds and currents would transport heat around the globe, creating a more even temperature profile. The fact that we see no such redistribution means LHS 3844b likely has little to no atmosphere at all. It is a bare rock adrift in the void. This airless world is also tidally locked to its dim star, meaning one hemisphere is in permanent, scorching daylight, while the other is locked in eternal, frigid night. Without an atmosphere to moderate temperatures or transport heat, the contrast between these two sides is absolute. The day side might be hot enough to melt lead, while the night side plunges to temperatures near absolute zero. What would the surface of such a world be like? Astronomers have a compelling clue. By analyzing the spectrum of light reflected from the planet, they found its surface is remarkably dark. The best match for that darkness is a landscape covered in basalt, the same dark volcanic rock that makes up the lunar Maria, the vast dark plains we see on our moon. This suggests a world possibly covered in ancient, cooled lava flows, a global desert of black rock under a starry sky that never changes. The discovery of LHS 3844b is profoundly significant. It tells us that not all Earth-sized planets are Earth-like. Some, especially those orbiting active red dwarfs, may have their atmospheres completely stripped away by stellar flares and radiation, leaving behind only a scorched or frozen skeleton. This raises crucial questions about the potential for life on other small, rocky worlds, particularly those we find in the so-called habitable zones of these common stars. If a planet has no air, no water, and no shield from radiation, its surface becomes a sterile monument. This world serves as a critical baseline, a reminder that size alone does not make a home, and that the thin, precious blanket of an atmosphere is the rarest and most vital treasure a rocky world can possess. The stark silence of an airless rock gives way to a world of roaring, incandescent motion. K2141b is a super-Earth sculpted from pure geological fury. This planet orbits so close to its orange dwarf star that a full year passes in less than 7 hours, a proximity that has forged one of the most extreme landscapes imaginable. Its surface is not land, but a single seething ocean of magma, hundreds of miles deep. This is not a planet with volcanoes. It is a planet that is a volcano. The cause of this global inferno is its profound tidal locking. One hemisphere permanently faces the star, a dayside blasted by relentless radiation where temperatures soar beyond 500 degrees Fahrenheit, hot enough to not just melt rock, but to vaporize it. The surface here is a churning, incandescent sea of molten silicate rock, a lava ocean with tides and currents driven by stellar heat. Yet cross the terminator into eternal night, and you enter a realm of profound cold. Temperatures on the night side plunge to hundreds of degrees below zero, a cold so intense it could freeze air solid. Here, the magma ocean does not simply cool, it solidifies into a global crust of black volcanic rock, a rigid shell over a still molten interior. This staggering temperature difference, thousands of degrees across a narrow band, powers a weather cycle of almost unimaginable violence. On the scorching day side, the intense heat doesn't just keep the lava liquid, it boils it. Minerals within the lava, like sodium, silicon monoxide, and silicon dioxide, are vaporized directly from the ocean's surface, launching into the atmosphere as a scalding metallic fog. Supersonic winds, generated by the extreme pressure difference between the two hemispheres, then scream across the terminator, carrying this vaporized rock to the frozen night side. As the mineral vapor hits the deep cold, it condenses. It does not form water droplets. It forms microscopic particles of rock, creating clouds not of water ice, but of solid silicate dust. And then, pulled by the planet's gravity, this rocky haze precipitates. It falls as a gritty, scorching sleet of tiny stones back into the magma ocean. In a more stable region, where the frigid nightside crust meets the ocean's edge, scientists speculate this falling rock sediment might even gather, forming a bleak, steaming shoreline of freshly solidified stone, only to be slowly dragged back into the molten abyss. This creates a complete, terrifying cycle of rock evaporation, atmospheric transport, and rocky precipitation. A lithic water cycle where the planet's very crust is continuously vaporized, transported, and then solidified again. K2141b is a world in a constant state of self-cannibalization, a roaring crucible where the ground, the sky, and the rain are all made of the same incandescent mineral soup. This relentless cycle of vaporized rock reveals a cosmos in constant violent motion, but sometimes that motion is measured in the slow, inevitable expansion of a dying star. The discovery of TOI 1789b offers a rare glimpse into the future fate of many hot Jupiters. This is a massive gas giant, an ultra-hot Jupiter, but it does not orbit a youthful, blazing star. Its host is a subgiant, a star that has exhausted the hydrogen fuel in its core and has begun to swell and brighten as it enters the final chapters of its life. This aging star has already started its transformation into a red giant, and its planet is paying the price. TOI 1789b orbits with a frantic pace, completing a full revolution in just 3.2 Earth days, clinging desperately close to its swelling sun. This proximity subjects the planet to a brutal and increasing barrage of radiation. The intense heat, estimated at over 300 degrees Fahrenheit, does not just warm the atmosphere, it fundamentally alters it. Observations suggest the planet's outer layers have become puffed up, its atmosphere inflated like a balloon over a flame. The extreme stellar radiation pumps energy into the gaseous envelope, causing it to expand to a size larger than typical planets of its mass. More than just bloated, this atmosphere is thought to be actively glowing. At these temperatures, molecules are broken apart into their constituent atoms, and these excited atoms emit their own light, creating a faint but detectable luminous shroud around the planet. It is not merely reflecting its star's light, it is shining from within due to the stellar assault. Studying worlds like TOI 1789b is like finding a fossil while the animal is still alive. It allows astronomers to watch, in real time, how planetary systems evolve as their stars age. We know that in about 5 billion years, our own sun will begin its subgiant phase, eventually expanding to engulf Mercury and Venus, and severely baking Earth. While our solar system lacks a close-in giant planet, many others do not. TOI 1789b shows us what happens to those worlds. Their atmospheres are heated, inflated, and slowly stripped away by the growing stellar winds of an elderly star. This planet is a canary in the cosmic coal mine, showing us the intense atmospheric escape and radical transformation that occurs when a star begins to die. It raises a haunting question for the countless hot Jupiters we have found. How many will be completely evaporated, leaving behind only a naked core? And how many will be entirely consumed when their star's outer layers finally reach out to swallow them whole? Yet even as some worlds lose their skies forever, others find a way to breathe again. GJ1132b is a story of cosmic resurrection. This Earth-sized planet orbits a quiet red dwarf star just 41 light-years away, a world that should be a dead, airless rock. Its close orbit bathes it in intense radiation from its star, and for years, astronomers assumed that any original atmosphere it had, a thick blanket of hydrogen and helium from its birth, had long since been blasted away into space. It was another candidate for a bare, scorched husk like LHS 3844b. But when the Hubble Space Telescope studied it, the data revealed something astonishing. JJ1132b was not naked. It had an atmosphere. This was impossible if it was a primordial shroud, so scientists were forced to consider a radical idea. This was not its first atmosphere, it was its second. The planet had somehow regrown a new sky. The composition of this secondary atmosphere was the key clue. Hubble's observations suggested it was not thin and tenuous, but surprisingly thick and rich with molecules that should not be there if the star had stripped everything away. The atmosphere showed strong signs of hydrogen, but not the free hydrogen from a young planet's birth cloud. Instead, this hydrogen was bound up in molecules like hydrogen cyanide and methane, and the atmosphere also contained a significant haze, a global layer of aerosols that scattered light. How could a world that lost everything now have a sky filled with these complex chemicals? The leading theory points to a deep internal furnace. Scientists believe JJ1132b is a volcanically active world. Its interior, kept hot by the relentless gravitational squeezing from its star in such a tight orbit, could be molten and churning. This internal heat would drive intense volcanic activity on the surface, cracking the crust open in countless fissures. From these volcanic vents, the planet would outgas, releasing trapped volatiles from its mantle. This outgassing would not release the original hydrogen and helium, but a completely different mix of gases, the byproducts of a geologically active, rocky world. The hydrogen likely comes from chemical reactions deep within the mantle, where water molecules trapped in rock are broken apart under extreme heat and pressure. The carbon for the methane and hydrogen cyanide could also be primordial, locked away in the planet's interior since its formation. So the picture that emerges is of a dynamic, living world in a geological sense. Its first puffy atmosphere was stolen by its star, leaving behind a barren globe, but deep within, its heart remained hot. Over eons, volcanic eruptions began to pump a new mixture of gases into the void, slowly building a second chance at a sky. This new atmosphere is toxic, a suffocating mix that would be instantly lethal to life as we know it. But its existence is a revelation. It proves that some planets are not passive victims of their stars. They can fight back with the forces of their own interiors, regenerating and renewing themselves against the odds. JJ1132b stands as a powerful symbol of planetary resilience, a world that literally built its own sky from the ground up. Resilience can take many forms, even a delicate and almost impossibly light one. WASP 107b is a planet that defies every instinct about what a gas giant should be. This world, orbiting a star 200 light-years away, has earned a nickname that perfectly captures its bizarre essence, the cotton candy planet. It is roughly the size of Jupiter, a colossal sphere you would expect to be massively heavy, yet it possesses only about 10% of Jupiter's mass. To understand how strange this is, picture the largest, fluffiest marshmallow you can imagine, then inflate it to the diameter of a beach ball. That is the density, or rather the lack of density, we are talking about. If you could find an ocean large enough, WASP 107b would float without hesitation. This extreme puffiness presents a serious puzzle for astronomers. How does a planet grow so large without gathering the mass to make itself dense? Standard formation models struggle to explain it. One compelling theory points to internal heat. The planet's orbit is slightly elliptical, meaning its distance from the star changes regularly. This creates a gravitational tug of war, stretching and squeezing the planet's interior with each orbit. This process, called tidal heating, pumps enormous energy into the planet's core, acting like a built-in furnace. That extra heat could be inflating the entire atmosphere from within, puffing it up like a hot air balloon and preventing it from collapsing into a denser, more compact state. Another possibility is that the planet's core itself formed in an unusual way. Perhaps it accreted its gargantuan gaseous envelope very late in the development of its solar system, from an unusually sparse or depleted disk of material, resulting in a massive but wispy atmosphere draped over a relatively small core. For years, these were our best guesses, but the recent gaze of the James Webb Space Telescope has pierced the planet's fluffy exterior to reveal new secrets. Webb's exquisite infrared instruments have detected the clear chemical signatures of both water vapor and sulfur dioxide in the atmosphere of WASP 107b. The presence of sulfur dioxide is particularly telling. This molecule is a strong indicator of active photochemistry, meaning the intense light from the star is constantly breaking apart molecules in the upper atmosphere, which then recombine into new compounds like sulfur dioxide. This detection proves that even within this ethereal, cotton candy world, complex and dynamic chemical processes are constantly at work, driven by the relentless glare of its sun. It is a world of profound contradictions, simultaneously delicate and gigantic, simple in structure yet chemically active, a whisper of a planet that somehow holds onto a complex and evolving sky. While cotton candy worlds stretch our imagination, the search also narrows to find a place that feels a little more like home. Kepler 1649c is a whisper of familiarity in the cosmic noise. Orbiting a quiet red dwarf star 300 light-years away, this rocky world is almost exactly the same size as our own, a near-perfect match in dimension. More importantly, it resides within its star's conservative habitable zone, that orbital sweet spot where temperatures could theoretically allow for liquid water to exist on the surface. Kepler 1649c receives about 75% of the stellar light that Earth gets from our Sun, a figure that suggests a climate that could be similar, if perhaps slightly cooler. The planet completes an orbit every 19.5 Earth days, a brisk year under the dim, crimson glow of its small star. This discovery sparked immediate and cautious excitement, as it represents one of the most Earth-like exoplanets ever found in both size and orbital energy. The possibility of a stable, temperate world with a solid surface and the right conditions for water is the holy grail of exoplanet science, and this world ticks many of the right boxes. Yet the optimism must be tempered by the harsh realities of life orbiting a red dwarf. These stars are notorious for their volatility, especially in their youth. They can erupt with powerful stellar flares, Sudden explosions of radiation that could bathe a close orbiting planet like Kepler 1649c in deadly ultraviolet and X-ray bursts, potentially stripping away any atmosphere and sterilizing the surface. Another major challenge is tidal locking. A planet orbiting so close to a small star is almost certainly gravitationally locked, meaning one side forever faces the star in perpetual daylight, while the other is trapped in endless night. This creates an extreme temperature dichotomy that could make the planet uninhabitable, with a scorching hot day side and a freezing cold night side. However, there is a glimmer of hope. If Kepler 1649c has a sufficiently thick atmosphere, winds could circulate heat from the day side to the night side, moderating the temperatures and potentially creating a twilight band along the terminator line where conditions might be stable. The presence of liquid water would depend entirely on the existence and composition of this crucial atmospheric blanket. For now, Kepler 1649c remains a compelling mystery, a tantalizing what-if etched in the data. It lacks the flamboyant extremes of lava oceans or diamond mantles, but its quiet, Earth-like proportions make it one of the most important targets for the next generation of telescopes, which will strive to sniff out the chemical signatures of its air, searching for the faint traces of water, oxygen, or other biomarkers that could hint at a world not just like ours, but perhaps even alive. But the skies of a distant world can hold treasures far more dazzling than steam or volcanic haze. HADP 7b is a hot Jupiter that has rewritten our understanding of alien weather, not with storms of rock or iron, but with a spectacle of gemstones. Orbiting a star over 1,000 light-years away, this planet is a blistering giant, tidally locked to its sun with a permanent dayside that glows at over 4,000 degrees Fahrenheit. For years, it was just another scorching ball of gas, until astronomers noticed something peculiar in the data from the Kepler Space Telescope. The planet's brightness was not constant. As it orbited, the amount of light reflected from its atmosphere changed in a rhythmic yet asymmetrical pattern. The brightest spot was not directly under its star, as one would expect, but was consistently shifted. This could mean only one thing: the planet's clouds were not stationary. They were being pushed. Powerful supersonic winds were racing from the scorching day side to the cooler night side, dragging colossal cloud formations with them. But these were not water vapor or ammonia clouds. By analyzing how the light scattered, scientists reached a stunning conclusion. The clouds on HADP 7b are likely composed of corundum, the very mineral that, when tinted with traces of other elements, forms rubies and sapphires here on Earth. Imagine the atmosphere of this giant world. On the searing day side, temperatures are so high that corundum exists as a vapor, a shimmering metallic fog suspended in the air. As these mineral-laden winds scream toward the night side, they encounter a steep temperature drop. The corundum condenses out of the air, crystallizing into countless microscopic particles. What forms is a global cloud deck not of water droplets, but of minuscule gemstones. The sky itself becomes a swirling, glittering haze of potential rubies and sapphires, reflecting the fierce light of the nearby star with a cold, mineral brilliance. These clouds do not produce gentle rain. They are part of a violent, global tempest where the winds, shaped by the extreme temperature contrast, constantly reshape these glittering formations, pushing the brightest patches across the terminator line in a perpetual, dazzling sunset. It is a world where the raw materials of royal jewels are nothing more than common dust, blown by eternal hurricanes across an incandescent sky. This discovery turns a scientific measurement into a scene of breathtaking beauty, proving that the universe's artistry operates on a scale where even the atmosphere can be a jeweler's workshop. Gemstone clouds hint at a world of fleeting beauty, but the next planet carries the weight of eternity itself. TOI 561b is not just another scorching super-Earth, it is a time capsule. Orbiting a star 280 light-years away, this rocky world completes its frantic year in less than 12 hours, so close to its sun that the surface is a molten hellscape. But its true significance lies not in its heat, but in its age. The star it orbits belongs to the Milky Way's thick disk, a population of ancient stars that formed when our galaxy was young and turbulent. Based on the star's chemical composition and motion, astronomers estimate this entire system is around 10 billion years old. That means TOI 561b formed when the universe itself was only about a third of its current age. This is one of the oldest rocky planets ever discovered. Its existence is a monumental discovery. For a world to be rocky, it must be built from heavy elements like iron, silicon, and magnesium, metals that were forged inside the cores of early generations of massive stars and scattered across space by their supernova explosions. The fact that TOI 561b exists proves that the necessary ingredients for terrestrial planets were already abundant and assembling into worlds barely a few billion years after the Big Bang. Rocky planets are not a late-stage luxury in cosmic evolution. They are a fundamental and early feature of our galaxy. This ancient world, however, is no cradle for life as we know it. Its breakneck orbit subjects it to savage stellar radiation, heating its surface to over 2,000 degrees Fahrenheit. If it ever had a substantial atmosphere or any water oceans, they were boiled away into the void eons ago. Today, it is likely a barren sphere of molten rock and metal, a searing relic of a bygone cosmic era. Yet its very presence raises a profound and tantalizing question. If rocky planets could form so quickly and so long ago, could life have also gotten an early start somewhere else in the galaxy? Could there be civilizations out there that are billions of years more advanced than our own, their origins lost in the deep time of the early universe? TOI 561b itself is a burnt cinder, but it stands as silent, scorching proof that the stage for life was set unimaginably early. The galaxy had the right materials and the right conditions to build Earth-like worlds almost from the very beginning, making the story of life potentially far older and more widespread than we ever dared to dream. The scorched antiquity of TOI 561b shows us planets that have endured, but one world has endured something far more catastrophic. WD 1856 plus 534b is a survivor on an almost unimaginable scale. This planet, a gas giant roughly the size of Jupiter, should not exist where it is. It orbits a white dwarf, the Earth-sized, super-dense corpse of a star that was once like our Sun. This white dwarf is the final, cooling ember, all that remains after the star exhausted its nuclear fuel, swelled into a red giant, and then violently ejected its outer layers, leaving only this incredibly dense core behind. That red giant phase is the key to the mystery. When a star like ours becomes a red giant, it expands to 100 times its original size, engulfing and vaporizing any planets orbiting within a distance comparable to Earth's orbit. Mercury, Venus, and likely Earth itself will be consumed in our own sun's future death throes. Yet here, a giant planet orbits this white dwarf incredibly closely, completing a full revolution in just 34 hours. It is so close that it must have been inside the star's MAXIMUM Chinese letter reach during its red giant phase. So how did it survive being swallowed? astronomers see two possible, equally dramatic escape routes. The first is a story of gravitational gymnastics. The planet may have originally orbited much farther out, well beyond the reach of the swelling star. After the red giant phase subsided and the white dwarf was left behind, gravitational interactions with other, now destroyed planets in the system could have sent this survivor on a slow, spiraling migration inward over billions of years, until it settled into the tight orbit we see today. The second possibility is even more breathtaking. Perhaps the planet was always on a slightly elliptical path. As the star began to swell, the planet's orbit could have been altered by the very process of the star losing mass, causing the planet's path to widen just enough to skim the outer fringes of the bloated stellar atmosphere without being fully engulfed. It would have been a cosmic dance along the edge of oblivion, a world surfing the titanic waves of a dying star's outer layers and emerging, scorched but intact, on the other side. The discovery of WD 1856 plus 534b shatters our assumptions about planetary system mortality. It proves that entire worlds can outlive the apocalyptic death of their suns. This opens a profound and haunting new chapter in astrobiology. White dwarfs are stable for trillions of years, far longer than the current age of the universe. If a giant planet can survive, then perhaps smaller, rocky moons orbiting that giant could survive as well. And if those moons retained or later developed conditions for liquid water in the distant, quiet future around this stellar ember, life could potentially find a way in the most unexpected of places, long after the galaxy's active stars have faded. This planet is not just a relic. It is a messenger from the far future, showing us that the end of a star is not necessarily the end of every world story. Our nearest stellar neighbor holds more than one secret. Just 4.2 light-years away, the red dwarf Proxima Centauri is already famous for hosting Proxima b, an Earth-sized world in its habitable zone. But astronomers suspected there was another, more distant companion in this cosmic backyard. After years of careful observation, they found it, a candidate planet now known as Proxima Centauri c. This world is a stark contrast to its inner sibling. While Proxima b hugs its dim star closely for warmth, Proxima c takes a long, lonely path. It orbits at a distance about 1.5 times that between Earth and our Sun, a vast gulf given Proxima's feeble glow. A single year on this frigid world would last nearly 5.5 Earth years, a slow, silent procession through the dark. Its estimated mass places it in the super-Earth category, somewhere between our planet and Neptune, but its environment is anything but Earth-like. At that tremendous distance from its cool, small star, Proxima c receives virtually no warmth. Surface temperatures are likely hundreds of degrees below zero, a permanent, deep freeze where even gases like nitrogen would solidify into ice. So what kind of world is it out there in the dark? The data presents two compelling possibilities. It could be a massive, frozen terrestrial planet, a super-Earth cloaked in a global glacier of exotic ices, with a rocky core buried beneath miles of frozen nitrogen, methane, and carbon dioxide. Alternatively, it might be a mini Neptune, a small gas giant with a thick, primordial atmosphere of hydrogen and helium that has frozen solid into an icy slush, creating a bizarre, frigid giant. Pinning down its nature is incredibly difficult because it was not found by the transit method, where a planet crosses its star. Instead, astronomers detected the subtle wobble of Proxima Centauri itself, the tiny gravitational tug exerted by this distant, massive world over many years. This radial velocity signal is faint, and requires painstaking analysis to separate from the star's own activity. The discovery adds profound complexity to our closest exoplanetary system. We now have a potential portrait of a binary planetary family with one world, Proxima b, orbiting in the tense, fiery zone where flares from the red dwarf could strip atmospheres, and another, Proxima c, drifting in the silent, outer darkness where everything is frozen in time. This raises fascinating questions about planetary formation around such small stars. How did a super-Earth or mini-Neptune form so far out in a disk that was presumably sparse? Could it have migrated inward from an even more distant birthplace? Proxima Centauri c is a ghostly signal from next door, a cold giant that reminds us even the nearest stars can hide worlds of unexpected scale and mystery, orbiting in shadows just beyond the light. The silent giant orbiting Proxima Centauri shows us planets can thrive in lonely darkness, but other worlds are born into a crowded celestial dance. TIZY 172900988b orbits not one, but two suns, in a configuration that pushes the boundaries of what we thought was possible. This gas giant was discovered in a system where two stars, similar in size to our own sun, orbit each other in a relatively wide embrace, completing a loop every 200 days. Most circumbinary planets we have found, like Kepler-16b, orbit very close to their twin stars, their paths tightly bound to the central pair. TIZY 172900988b is different. It follows a wide, stately path far beyond both stars, taking almost a full Earth year to complete a single orbit around the combined mass of its two suns. Finding this distant giant was a feat of astronomical detective work. The TESS satellite observed the system, watching for the telltale dip in starlight that occurs when a planet transits or passes in front of its star. But the data was a tangled mess of dips and variations. Astronomers had to unravel a signal where the planet was transiting not one, but two different stars at different times and from different angles, as all three bodies moved through their complex gravitational ballet. It was like trying to follow the shadow of a single bird cast by two moving spotlights. Decoding this intricate pattern confirmed the planet's existence and its wide, stable orbit. This discovery is profoundly important because it proves that planets can form and persist in the expansive outer regions of a binary star system. For a long time, we thought the gravitational turbulence of two stars would disrupt planet formation beyond a certain distance, or that any planet that did form would be quickly ejected into the void. TASI 172900988b defies those expectations. Its wide, peaceful orbit shows that stable zones for planets exist even in these complex gravitational landscapes, zones where a world can enjoy double sunrises and sunsets without being torn apart. This expands the cosmic real estate where we might search for habitable worlds, suggesting that even in systems with multiple suns, there could be tranquil, distant orbits where smaller, rocky moons might find a stable home under a forever-changing sky. After the grand cosmic dances of binary suns and distant giants, we find a quiet promise much closer to home. The final stop on our tour of 25 bizarre worlds brings us to a star so faint it was only discovered in 2003. And the two Earth-sized planets that may just be the most welcoming we have yet found. Just 12 light-years away, a dim red dwarf named Tegarden's star holds a secret two rocky worlds, Tegarden's B and Tegarden's C, each with a mass eerily similar to our own planet. They do not orbit in a frantic blaze or a frozen waste, but within their star's conservative habitable zone, the orbital region where liquid water could theoretically exist on a planet's surface. This alone makes them extraordinary, but it is the nature of their sun that makes them truly special. Teegarden's star is an ultra-cool red dwarf, and it is remarkably calm and quiet. Unlike the violent, flaring red dwarfs that threaten to strip atmospheres from worlds like Proxima b, this star exhibits very low magnetic activity. It is a gentle ember in the cosmic dark, significantly reducing the threat of the sterilizing radiation bursts that plague so many other promising systems. This stability is a game changer. It means these worlds, if they possess atmospheres, could have held onto them for billions of years. Teegarden's B, the inner planet, is particularly compelling. It has one of the highest Earth Similarity Index scores ever calculated, a measure that compares a planet's size, density, and received stellar energy to our own worlds. It completes an orbit in just 4.9 Earth days, but because its star is so cool and dim, that proximity still places it squarely in the habitable zone. Its sibling, Teegarden's C, orbits farther out in a colder, more Mars-like region with a year of 11.4 days. The possibility that both are temperate, rocky worlds is a stunning one. Imagine a system where two Earth-mass planets, possibly both with solid surfaces and moderate temperatures, circle the same gentle star. They are likely tidally locked, with permanent daysides and nightsides, but a sufficiently thick atmosphere could circulate heat and create a band of potentially habitable twilight along the terminator line. For scientists searching for life, these are not just entries on a list, they are top priority targets. The next generation of telescopes will aim their most powerful instruments at this nearby, quiet system, hoping to catch the faint chemical fingerprint of water vapor, methane, or even oxygen in their skies. They represent a profound shift in the narrative, from the bizarre and hostile to the potentially familiar and nurturing. After a journey through lava oceans and diamond mantles, gemstone skies and evaporated giants, we end with a whisper of possibility, a reminder that amid the cosmic spectacle of extremes, the universe may also craft quiet, steady worlds not so different from our own pale blue dot, waiting in the gentle light of a nearby star. This voyage across 25 alien worlds reveals a cosmos of staggering diversity and relentless creativity. From the diamond heart of 55 Cancri E to the sapphire clouds of HDP 7b, from the molten iron rains of WASP 76b to the ancient scorched stone of TY 561b, each discovery shatters another assumption. We have seen planets evaporating, planets being eaten, and planets rebuilding their own skies from volcanic breath. We have encountered worlds lighter than cotton candy and cores heavier than entire solar systems, all orbiting stars both living and dead. This is not science fiction. It is the new map of our galactic neighborhood, drawn in data points of light and shadow. None of this would be visible without our mechanical eyes in the dark. The silent vigil of Kepler, the infrared gaze of Spitzer and Hubble, and now the transformative power of the James Webb Space Telescope have turned distant pinpricks of light into stories. These instruments do not just take pictures, they perform cosmic chemistry, sniffing the atmospheres of worlds 1,000 light-years away to tell us if their skies are made of vaporized rock or toxic haze. They measure the wobble of stars to reveal the gentle tug of hidden giants, and they watch for the faint, rhythmic dimming that betrays a planet's passage. Every bizarre world on our list is a monument to human curiosity and engineering, a testament to our species' drive to look into the night and ask, what else is out there? And this is only the beginning. The next decade promises telescopes with vision so sharp they might one day glimpse the pale blue dot of an Earth twin, analyzing its atmosphere for the signatures of life itself. We stand on the threshold of answering the oldest question: are we alone? Each strange and wonderful world we find expands the possibilities for where life could take root, in the sulfuric clouds of a gas giant, or deep within the subsurface ocean of an ice moon. The universe has shown us it can build planets from every element in every configuration imaginable. So why not ones that breathe and grow? Your tour of the cosmos is complete, but the conversation is just starting. Look back over these 25 bizarre worlds, from the glittering to the grotesque, the ancient to the apocalyptic. Which one captured your imagination the most? Was it the diamond planet, the world with sideways glass rain, or the survivor of a stellar explosion? Share your favorite in the comments below, and let us know which cosmic mystery we should explore next. For more journeys to the edges of discovery, make sure to subscribe. The universe is vast, strange, and waiting.